Hello everyone. Should be a fairly short lecture today. We're going to continue talking about gears. First, we'll have a homework. So homework 9, that's going to be due this Friday for those of you that are actually in the class. So it's going to be Cam's homework. There's kind of a lot going on in this, so I included a sample from a previous semester. So you are tasked with designing a critical extreme position intake cam profile for a car. This is going to be the intake valve, not the exhaust valve. The exhaust valve would actually be a little earlier in the graph than this, like exhaust would be, I don't know, somewhere like that. This one's pretty narrow here shown. I've actually made the values a little more realistic in this one, so your cam lobe should look a little better than my cam lobe here for the example. So it's dwell, rise, dwell, fall, dwell. So it needs to dwell at 0 for 300 degrees, so S equals 0 for 300 degrees. It needs to open, so beta would be 150 degrees. It's going to dwell open for 10 degrees, so it's going to be dwelled up here at 0.475 inches on the S for 10 degrees. It's going to fall over 150 degrees, so beta for the fall would be 150 degrees. And then it's going to stay closed until we get to 720 degrees. So take 720 minus 150 times 2 minus 10 minus 300. That tells you the dwell at the end. I want an SVAJ diagram. I want a cam lobe profile like this one. That is a radar chart in Excel. If you have S plus the prime circle radius plotted for every degree and then insert a radar chart for that column, you'll get this. It does have to be plotted for every degree though. And you don't have to offset this for the roller follower. So this would be the prime circle. This would be the pitch path for it, not the actual metal. Offset's a lot harder to do. Plot of the pressure angle versus cam angle. That's this. Plot of instantaneous pitch radius for a 1/4 inch follower. That's this. So your graph should look fairly similar to this. This is a cycloidal function. So you'll have to go back to CAMS 2 and use the equations for the rise, and then also when you do the fall you'll have to make sure you use the modified equations for the fall. There's a slide on that. This is a pretty tricky spreadsheet assignment. You could do it in a computer program or something like that. You can't do this one by hand, so you either need to do this in a spreadsheet or a computer program. And you've got to do this piecewise. That's the main hint I'll give, is you can't just, there's not one function that's valid from here to here for these, right? You have to break it into 5 different pieces, you know, for the dwell, rise, dwell, fall, and dwell. And you have to figure out how to stick those pieces together. So you've got what the answer should basically look like. Your diagrams will be a little bit different. So I think that's enough to go on. So this is a pretty big assignment. I would not wait to get started on it. Okay, continuing talking about gears. This was a trip I took down to Florida a few years ago, and on the way down I stopped by and saw the Battleship Alabama, which is in Mobile, Alabama. And if you're ever in the area, those of you mechanical engineers out there, you really owe it to yourselves to go see what a World War II battleship looks like. It's pretty well the pinnacle of mechanical engineering. There's still some electrical stuff that started to get introduced there, some motors and servos and things like that. But by and large, it is a mechanical system. Now, most things nowadays, there's still some big chunky mechanical parts like gears and things like that, but all the control systems are going to be electrical. So, it has a displacement of around 45,000 tons, and yes, that's the same as the weight. Displacement and weight are equal to each other. This is the amount of water this displaces, which is equal to the weight. Well, 4,000 tons. Tons of, that's interesting. Tons, not a ton would be a unit of weight, wouldn't it? Having an existential crisis about units, because that's 2,000 pounds force, right? So yeah, tons would be a unit of weight. So that would be, the ship would weigh an equivalent of 45,233 tons of water. Power, 130,000 horsepower from 4 geared steam turbines. So this was powered by burning oil and burners. That made, the heat from that was used to boil water. To make steam. Steam was run through turbines, the big gears to reduce the speed, the high RPMs of the turbine down to the low RPMs of the propeller. So that's what you see here, is these big, very precisely made helical gears. So the fact that they were making these things, as precise as they were and as strong as they were, back from the earlier days of steam geared turbine battleships like 100 years ago. It's pretty amazing. This is pretty sophisticated gear, pretty precise gear. But that's not the only application of gears. So one of the big problems in talking about the battleship era is hitting the other ship, because your ship is moving, the ship you want to hit is moving. You have all sorts of atmospheric effects, aerodynamic drag of the shell. You're going to have to factor that in. You can't assume it's just going to travel in a perfect parabola. So to do the actual path with air resistance, you actually have to do integration. So they made mechanical systems that would do integration. They made mechanical systems that would do addition, subtraction, multiplication, division, integration, differentiation, and they put these things all together in these boxes and made mechanical computers for calculating what angle you needed to fire, what elevation, what timing. They calculated all of that stuff, and then that got used to actually fire the big guns. So I believe these are the Mark 8 range keepers. There's one for each turret here. I think there's a redundant set somewhere else too, because there was a lot of redundancies in these battleships. In case this part got blown up, you could still fire the guns. You can fire the guns locally within the turret. You can fire the guns in, this is the fire control. I think there was another fire control you could fire from too. You could fire guns from all over the place in case part of the ship got blown up. This was in a heavily armored area, though, in the guts of the ship. So if you're touring a battleship, make sure you get down to this area. It's pretty cool. So anyway, these things would input your target and course, your course and speed, your target's course and speed, wind speed and direction, the rate at which range is changing, deflection rate, course change, time of flight, range and spot corrections, and this thing would output range versus time, the change in range, and the time it takes for salvos to land, so it's time it takes for the shell to get from here to where it impacts. Some of these things are inputs and some are outputs, right? This would be input, these would be more output things down here. But point is, it tells you where to aim the guns, how to elevate them, and tell you when to fire. And it worked pretty well. Actually, it worked better than pretty much any other system in the world at the time. And by the end of World War II, our battleships, while not the biggest and most powerful, Japan built two that were bigger and had bigger guns than Iowa class, and which is the Alabama is one class before the Iowa class, the South Dakota class, but pretty similar. Actually, not that much of an improvement, other than the Iowas are a lot faster. But the fire control systems were amazing. Combining this with radar, these things were incredibly accurate, could fire in the dark and in any kind of weather, and it was pretty incredible what they could do. Now, of course, all of this is an Arduino is orders of magnitude more powerful than all of this thing. So we live in a totally different era nowadays. So back then, this is what they had. So they made mechanical computers. There's a whole bunch of gears in there. And they made this stuff with pretty crude manufacturing technology. Right? If you look at the machine shop in a battleship, there's no CNC machines because that stuff didn't even exist yet, right? So all these intricate parts had to be made on manual equipment, which makes it even more amazing. Okay, so enough talking about battleships in World War II. Pressure angle. So we talked a little bit about pressure angle in the previous lecture in Gears 1. So these are set by the manufacturer, and because you have to retool your manufacturing equipment to make different pressure angles, there's usually only a few pressure angles. There's 14.5, there's 20, and sometimes 22.5 degrees. You don't see 22.5 that much anymore. In fact, you pretty well see 20 is the most common, with some 14.5. You can see the 20 has got fatter teeth here, stronger teeth. So you get a little bit more spreading force though from it, which your shaft has to resist, your bearings have to resist it too. So it's not all upside in the 20 degrees, but it's pretty common now. So that's set by the manufacturer, and that's something you just don't have any ability to get custom pressure angles unless you're wire EDMing gears, which you probably shouldn't do unless you're making something very one-off and specific that doesn't exist out there. If you can get a gear from somebody that makes gears for a living, do that. Don't try to make gears. That's my recommendation. I see a lot of students make gears for projects, and it almost never works very well. Two meshing gears have to have the same pressure angle. This gear and this gear can't mesh with each other. Bad things happen. As you change center to center distance, the pressure angle will change. Here's an equation for calculating that. When selecting gears, there's an ideal center to center distance. That is the pitch radius of the smaller gear plus the pitch radius of the bigger gear. That will be the nominal center to center distance that gives you the listed pressure angle. Any deviation from that, according to this equation, that'll give you the change in pressure angle. So higher pressure angles usually mean bigger, stronger teeth. Oh, that's moose. But it also means more spreading force. So there's a downside to it as well. And then here's the equation down here where phi is your nominal pressure angle. This is your percent change in center to center distance. That gives you your new pressure angle down here. So they can use that to calculate new pressure angle. Changes to the center to center distance. Backlash. So backlash is important in gears. So backlash is this distance right. Oops. Let me fix that. Sorry about that. Backlash is this distance right there. And there's got to be some backlash for involute gears. Now for cycloidal, it's a different thing. They really don't, the way they operate, backlash isn't important. But for involute gears, you need a little bit of backlash. So it's required for normal operation. You don't want to get completely rid of backlash. There's some applications where you want to try to minimize it, but you know, each gear set needs some backlash to operate. So backlash is only really a problem when you change direction. So right now it looks like, you know, this gear is driving this one this way, and so they're touching right there, and so this backlash is clearance right there on the back side. And you can see if I reverse direction of this gear here, there's going to be a time period where that gear accelerates because it's not loaded at all. It's just loaded by the inertia of that gear, and it's going to slam into this gear and reverse its direction. You can see that's going to be stressful. It's going to cause noise. It's going to cause wear. It's going to cause you know, vibrations. It's going to cause problems. So we want it to be as small as necessary, essentially. So usually the rule of thumb for backlash, but you know, we only really care if we have torque reversals. If we don't have torque reversals, it's not that big of a deal. So and noise, wear, extra stress, yeah, those kind of things happen when you have too much backlash and you have torque reversals. So here's a plot from this is American Gear Manufacturers Association. I believe is what AGMA stands for. Diametral pitches, which we'll talk about in a bit, center to center distance. So if you talk about something like a differential gear, a ring and pinion in a car, you'll find it somewhere in this range of 10 to 20 thousandths of backlash. So that would be 10 to 20 thousandths of an inch. Backlash here would be ideal. And so for any kind of gear set like that, you're usually going to get some specification on backlash. If not, you can look it up in a table. So, and as the gears get bigger, the backlash gets bigger too. So it's normalized to the diameter, the nominal center to center distance here, and it changes a little bit with pitch as well. You can see some of these there's not really gears. You know, there's not this pitch in small gears. There's not this big pitch, and so there's not a lot of teeth on giant gears. So there's kind of a diagonal bias in this chart here. Backlash changes with center to center distance. That's how you can adjust it. If you move the centers farther apart, you get more backlash. If you move them together, you get less backlash. So this is an approximate form here, where the angle in backlash, which I'll have to convert back to the linear distance, some constant to make the units work out, change in center to center distance, tangent or pressure angle over pi times pitch diameter of the gear being measured. This is going to give you arcs, which is 1/60th of a degree. I hate equations like this that have units built into them. So if you're going to use this, be careful, watch your units on it. So this is percent change, so it's fine. This is pitch diameter here, so it needs to be in inches, and this will give you arcs in 1/60th of a degree. So in servo mechanisms like a CNC machine, backlash can cause position error. It can also cause, if you have lots of torque reversals, because your input might be moving but your output's not, because a backlash is kind of like a dwell, and the system doesn't account for that, you can get all sorts of weird and interesting errors in your control, including hunting behavior, where something won't ever move to a position and stop. It'll sit there and wiggle around a little bit at the position. It can cause positional accuracy error. That's something backlash will be a big problem in manufacturing equipment. If you're trying to feed in and then reverse direction, it'll be a period of time where your servo's moving but your output's not. And if you're measuring on the servo with like an encoder, then you're not capturing what the backlash does. So you'll actually have to program how much backlash there is in the machine into the controller. They make anti-backlash gears. You have to be very careful about what that means. So unfortunately, I can't show these videos again for copyright reasons, but for anyone watching this video, stop and watch this. I'll post a link down in the description. It shows different anti-backlash gears. You see gears like this that have springs in them. So these are smoother, but they don't eliminate backlash. So what happens is you have a gear that's going to ride on. So on the mating gear, this is going to ride on one tooth. This is going to ride on another tooth. And so there's no backlash, but what's going to hold these things apart are the spring tension in here. And so if your torque is high enough to compress those springs, you're going to get some backlash, right? There's going to be play in the system as these two gears move relative to each other. So they're smoother, they're quieter, but you still have backlash because it's a spring rate, right? So any amount of, I mean, they'll be preloaded at some point in time, but when you're moving a lot of torque through these things, you're going to stretch these springs out, and it's going to be hard to get a spring with enough preload to completely eliminate backlash. They make gears like this that you phase, and then there's bolts that you clamp these things together. Those are better. And you're still going to have some backlash, but it's going to be very, very small. So those are probably the best true anti-backlash gears. So the ones where you can phase the two halves and then lock them together with some kind of bolts or something. Those work pretty well. The spring ones you got to watch. They're going to be quiet and smooth, but you still might end up stretching those springs a bit and get a little bit of actual backlash, even though it doesn't seem like it. So you gotta be careful with anti-backlash gears. They make all sorts of systems and CNC machines like ball screws that are preloaded that eliminate backlash and still work smoothly. Those work really well. So those are kind of a different thing. But when it comes to gears, there's the spring type ones. And then there's the ones where you phase and lock down. So again, watch this video. It's a great video that shows these different kinds of gears. Checking backlash. This is a video of someone with a homemade CNC router trying to measure backlash. And one mistake they make in this video is they sit there and go back and forth and back and forth and back and forth and back and forth and then back to the original position, and with a dial indicator measure the delta. And it ends up right back where it was. Well, that's not checking backlash. So in backlash, you need to go this way, and then you need to reverse, and then you need to see one reversal and see where you're at. Because backlash is not cumulative. So what's going to happen is it's going to feed this way, and then there's going to be this dead period where I move the input, but the output doesn't move, and so when I come back, I'm going to end up just a little bit short. That's the backlash. Now what happens when I try to feed this thing back the other direction is I'm going to start feeding it and I undo this backlash, and then I move back to here, and then I come back here, and then I undo the backlash, and the end result is if I do multiple cycles, the error doesn't accumulate. It's just it just happens one cycle and then it unhappens the next cycle. So it only happens on reversals, and so if you reverse twice, the effect goes away. So it's not an error that accumulates, which is great. It means if all I can do is if I measure the backlash, program it into my controller, and compensate that in my motion, I don't lose any accuracy due to backlash as long as I measure it and account for it. Errors that accumulate, like when you're doing integration mathematically in a digital computer, you lose some information when you integrate. You lose precision at some point in time because you're representing things as a finite number of bits. In that case, sorry, I got distracted. So in that case, you're actually losing information, and your integral gradually gets more and more wrong as time goes on. That's a problem. That's an accumulating source of error. If you're using steppers and you miss steps, that's an accumulating source of error. So those are the things that are really scary in servo control machineries when you have accumulating error. Error that just happens at a step and then it gets undone like backlash. It's a deal. We have to worry about it, but it's relatively easy to fix. Nomenclature, we've covered most of this. Addendum, that's the amount above the pitch circle. Dedendum, that's the amount below the pitch circle. Tooth thickness, that's tooth thickness. Actually, sorry, no, that's not tooth thickness. This is tooth thickness. So that's face width. This is face width. This is tooth thickness. So that is the length, the width, what's the word? Thickness of the tooth along the pitch circle. Space width, that is the same thing along the empty space instead of on a tooth. Those should be different by the backlash. So space width should be tooth thickness plus backlash. And then, yeah, face width is that. Anything else? Yeah, so down here you can see there's a clearance. This has just been, offset down an amount, and then a fillet put down here. You could just do this as a whole fillet if you want to as well. It doesn't really matter. There's just clearance so that the other gears teeth don't dig into that area. And some gears it's required, some it's not. Pitch. So pitch is important. When you buy gears, you need to know the pitch of the gear you're buying. There's all sorts of different ways to report it. Diametral pitch is what we use here in the U.S. Module is what they use in metric land, which we use here in the U.S. too. We use both. So here in the U.S. you'll need to know both systems. And of course they're the inverse of each other, which is great. Circular pitch you don't see a lot except in calculations. That's the length of arc from one point on one tooth to the same point on the next tooth. That defines the tooth size. So that's pitch diameter, number of teeth. So pitch diameter of the gear times pi over n, that is the circular pitch. Base pitch, again, you don't see that a lot in tables and things or when you're buying gears, but it's used in calculations. It's circular pitch times cosine of the pressure angle. That's distance along the circumference. The important one, diametral pitch. That is number of teeth divided by pitch diameter. So that one's what you see. When you buy a gear by pitch and it's like an 8-pitch gear, that means there's 8 teeth per inch of pitch diameter. So a gear with a 1-inch pitch diameter and an 8-pitch has got 8 teeth on it. If it's a 2-inch pitch diameter, it's got 16 teeth on it. You can relate this back to circular pitch very easily just by taking pi divided by circular pitch. But when you buy gears, you're buying by diametral pitch. In metric, it is obviously the opposite, where it's the diameter in millimeters divided by number of teeth. So which one's better? There's not anything better here. So sorry, metric snobs, that they're equally bad or equally good. They basically are just the inverse of each other. So there's no inherent improvement in one versus the other. These don't have any kind of units that are called out in metric. Here it's millimeters per tooth. Here it's teeth per inch. So we can use the diametral pitch to relate we can use number of teeth to find velocity ratio, which if you're around gears a lot, you already know you can count teeth and divide the ratio of teeth to get a gear ratio, but we'll prove it real quick. Diametral pitch is number of teeth per inch. We can solve this equation for the diameter, which is number of teeth divided by diametral pitch. We can take our equation for velocity ratio, which we found from doing, V times R equals, making a mess here. Omega times R is omega times R. We used that to find the velocity ratio, and we got a ratio of the gears radii. We can multiply those by 2 to get the diameter. We did that in like lecture 1 for gears. And we get our velocity ratio as a function of the diameters. For each of these diameters, use this equation to plug in the number of teeth for each gear divided by its diametral pitch. Assuming these are the same, those will divide out. They have to be the same. You can't mesh two gears that have different diametral pitches. They're not going to work with each other, so they'll eat each other. So those will be the same. What that means is I can find the velocity ratio from counting the number of teeth on the input gear and the number of teeth on the output gear. That's the easiest thing to count. Measuring this diameter is hard, remember, because that's on the pitch diameter, and there's no metal spot to get your calipers out and measure. This you count, and counting is easy, right? So now, I don't know what it is about count teeth on gears, but you always miss one or two when you count. Especially on a gear that's got like 50 teeth on it or something. I've never counted teeth the first time and got it right. It always changes after I count it 2 or 3 times. So I don't know what to say on it, but mark a dot to start with on when you're counting teeth. count it once and then count it 2 or 3 more times to make sure your number doesn't change, and keep counting until your number doesn't change is be my advice, because something about it, the teeth all look the same. It's easy to miss or count an extra one when you're counting teeth on a gear. But once you've counted the teeth, you can do the simple ratio to get the velocity ratio. Torque ratio is going to be the inverse of that. Remember the same caveats on torque ratio. This is perfect efficiency, no energy storage. This is geometric. This is true. This is assuming there's no mass, assuming there's no efficiency. Pitch as it changes. So as pitch gets bigger, the teeth get smaller. So that's teeth per inch. So a bigger number means more teeth per inch. So 8 means there's twice as many teeth per inch of pitch diameter. So it gets bigger, the teeth get smaller. Modules the other way around. It's millimeters per tooth. So as it gets bigger, the teeth get bigger. So they go in opposite directions. So how do I pick? What's an appropriate tooth size? So we need to talk about average number of teeth in contact to answer that. To do that, we need to calculate this value for Z first. Z is length of action. It is the distance from there to there. That's length of action. So that is Z. We can calculate it from our pitch radii from the 2 gears. Again, pinion's the smaller one. If they're the same size, it doesn't matter. They're both gears. Addendum for pitch of pinion and gear. Pressure angle, center to center distance. Again, these things you already have. So you can easily calculate Z, length of action. We use that to calculate the average number of teeth in contact. That is Z divided by base pitch. To get that in terms of diametral pitch, because we don't always have base pitch, we take diametral pitch times Z divided by pi times cosine pressure angle. That gives us the average number of teeth in contact. So in general, more teeth on the gear, smaller teeth for the same size pitch diameter, more teeth in the gear means you're going to have more in contact on average. More addendum means you're going to have more in contact in average, right? So as these things on the plus side here go up, you're going to get more teeth in contact. So this is really important. If the teeth are too big, this number can actually go down below 1. So for increasing the size of the tooth for a given pitch diameter, at some point in time you're going to get to a point where this average number of teeth in contact is less than 1, and that means, so your teeth, it's an integer thing, right? 0 teeth are in contact, 1 tooth's in contact, 2 teeth are in contact, 3 teeth are in contact. So if the average is less than 1, that means at some point in time there's 0 teeth in contact, right? That's one of the fundamental rules of calculus, right? If the average is something, there's got to be something less than that and something greater than it, right? So if the average is less than 1, that means at some point in time there's 0 teeth in contact, and that means that the teeth gears aren't meshing and it doesn't work. So this has to be greater than 1. You don't want it to be 1. You want some margin on top of it. So you need it to be greater than 1. So the minimum acceptable is around 1.2, preferred's around 1.4, usual range between 1.4 and 2. So this is really where you want to be. So that determines the biggest teeth you can use for a given pitch diameter. Usually they're going to get a little more expensive as the number of teeth go up usually, just because they're harder to manufacture. So that's sort of how do you pick the biggest possible tooth you can get by with. Again, there's not a huge reason to go much past 2. It's hard to get much past 2. So 1.4 to 2, that's what you mainly need to check. That determines if your teeth are the correct size. Okay, so that's it for this lecture. We'll continue talking about gear types in the next lecture. Make sure you get started on the homework. It's going to take a little bit of time. As usual, send me questions via email. That's it for today. Thank you.